Thank you very much for joining me here. So I will be talking about writing your own type checker plugins. So in recent years, already quite a few years by now, but there's all these nice extensions that we have, like type families and data kinds, that we can do quite a bit of serious work, like dependently typed programming work in Haskell. We don't have to use Agda or anything. We can just, use our tools that we love in the language that we love. But as you play around a bit with these things, with these type indexed lists or whatever, you find that it requires you to be a bit more clever about arranging your types and whatnot, which I think is not the right way to think about it, that it requires more cleverness from the programmer. It should require more cleverness from the type checker, because when you do this, there's an awful lot of bureaucracy that you're now suddenly faced with. Like a lot of these, as we'll see in this talk, a lot of these small things that you need to convince the type checker of, that when you look at it as a human being, you say, oh, this is trivial. Everybody sees that this is true. So that's something where type checker plugins come into play. It basically provides us with an interface to teach our type checker new tricks and make it a bit more clever so that we don't have to be clever and actually can think about the real problem that we're trying to solve when we're programming. Okay, so the prime example of any data type, I guess, is the natural numbers. And with data kinds, we get this nice concept called data type promotion, that we can just write this value level ordinary data type, and we also get versions of the same thing, the same structure at the type level. Sadly, for functions, these are not yet promoted. So if we want to write a function on sort of the type level variant of these natural numbers, then we have to use a type family. So if we want to add two natural numbers, we do the usual thing that we recurs on the first argument, and then, we just define addition in the normal way we always do. Also in practice, you shouldn't be doing this. You should be using nat from this module called GHC.typelets, which is faster and better and everything. But the problems that we will see later on, you will get the same or very similar problems when you use the natural numbers from typelets as you do with this, as the one that is defined here. Okay, so we can use these type level natural numbers to define length indexed lists. So a list that takes an index that tells us how long the list should be. We just say that an empty list, it's has length 0, and if we cons something to that list, we increase the length of that list by 1. And then we can use this definition to define addition of vectors, addition of these length index lists, just in the same way. Like this part here looks exactly the same as it would look like if we write it for old-fashioned lists, but the type here is a bit different. It tells us that the resulting list should, unsurprisingly, have the length, which is the sum of the two lists. Also note that actually we're kind of writing the same program here. Like we pattern match on the 0 case, the empty list case, and give the second argument back. And here we have like the recursive case. And you can see that there's a lot of similarity. And this coincidence also means that this actually type checks. So in this case, everything is fine. You get the type that you want it to be, and it's all fine and dandy. But then, we have quick check. We can't yet have all these properties in our type system yet, so we have to write these quick check properties to get some feeling of whether our program satisfies some rules. So we might want to write these two laws for our vector appending. So we expect that if we append something on the beginning, if we append the empty list to the beginning of some list, then we get the same thing back. If we do the same thing, but on the other hand, we also expect the same thing to get back. But there's a problem here. So left unit, it's no problem there. Just type checks, and GHC is happy with you and your code. But the right unit definition doesn't quite type check. It says that we expect this vector of length n, but actually we get a vector of length n plus 0. And as a human being, you look at it and you're like, yeah, but duh, it's like n plus 0, that's the same thing as n. So how can we convince our type checker of this? And so, yeah, so if we look at it a bit more closely, if we look at the type of v-append excess of nil, we see this n plus 0 popping up here. And looking at the definition, you see directly that 0 plus n equals n. But if we try to add n, where n is a variable, we don't know anything about it other than that it has type nat, we can't reduce that further if we only have this definition of add here, because, yeah, it's blocked. We can't reduce it any further. So yeah, if you do dependently typed programming, you also have this problem in Agda. You have this problem all the time that you think, oh, I can put everything in my type index, all these invariants, lengths, and balancedness, and whatever. But often we find that even simple things, like simple expressions like we saw in the previous slide, they don't type check. And we have to convince the type checker, we have to give some proof that these equalities that do not hold by definition actually hold. Because if we go back to this example of this add 0 to n, if we plug in any concrete n, it's all fine. It's only, and we can also prove, inductively on paper that it will always be equal to n. But yeah, it doesn't hold by definition, so your type checker just throws its hands up in the air and, yeah, I don't know, I can't see that these two things are the same. So when you do dependently typed programming, you often find yourself rearranging your types and your data types and indices in such a way, you write your functions in such a way that all the equalities that you care about when you use these functions, they hold by definition. And yeah, this is kind of a pain. And it also requires cleverness from the programmer as opposed to cleverness from the type checker, because yeah, you should be solving real problems and not these kind of trivial bureaucratic issues. So that's where type checker plugins come into play. So if we look at GHC's type checker, at the basis of it, there's something that walks through your code. It collects a whole bunch of constraints, some that you give yourself, like I want this type variable A to be of class EQA, stuff like that. So it goes through your program, generates a whole bunch of constraints. It tries to solve them. It might generate some new constraints whilst it's trying to solve them to simplify things, and does this a couple of times. And then at the end, it ends up with either saying that every constraint is just solved, it's all fine, and your program type checks, or there's some that can't be solved, and then GHC tells you that your program, that it thinks that your program is not typed correctly. So type checker plugins allow us to deal with this loop of generating and solving constraints. It allows us to write some code that's then plugged into this loop and iteratively called. So it really, with these plugins, you really interact with the type checker. So it's not just first GHC's type checker and then your code. It really becomes part of the whole type checker. which is quite powerful. So what do you have to do to write such a type checker plugin? You write a Haskell module, unsurprisingly, and you use the GHC API. So GHC, as opposed to just importing GHC itself and depending on this huge library and executable and whatnot that takes quite some effort to build. There's this nice API that just exposes those things that you might want to care about if you use parts of GHC, such as the type checker plugin infrastructure, or I don't know, parsing files or whatever. It exposes that through this API. So there you don't have to worry about build systems, or it all just works as any old Haskell package. And then the users of your type checker plugin, they just use this command line option to GHC saying, okay, -f plugin, load this type checker plugin that's given by this module name. And it's also something that you can do on a per module basis. So you can just use the pragma variant of this command line option. So you can say, okay, only in this module, I want to be using this type checker plugin, and then my other code will just work as it always did. And so the code that we will see in this talk, it will mostly depend on the GHC API, but there will also be some bits and pieces from Christian Buy's GHC TC plugins extra, which provides some extra tools that just make life a bit easier and a bit less bureaucratic when dealing with the GHC API for type checker plugins. So what's this interface? So we have to give a module that exports this record. So most importantly, we have to give a field of this type. So we take in some command line options, and then we return this maybe TC plugin. So what's this TC plugin? There's this existential type S, that's sort of our plugin context that we get to choose ourselves as the type checker plugin implementer. So that's where we can keep any piece of data that we need whilst we are solving our constraints. So this init function here, TC plugin init, that runs the TC plugin monad. Sorry, it's a TC plugin monad action that gives us back the initial context. Then there's some solver. So this is really what we care about and what we'll spend the most time looking at in this talk. And then there's some cleanup function afterwards, after we've solved all the constraints and run all the iterations of the type checker. And then this is what we will be looking at quite a bit, the result that we have to give back to GHC, and also this CT thing. There's a reason why it has a short name, because you use it everywhere. So it's the type of constraints, and that's really what we're dealing with. We have to recognize constraints and maybe generate new ones. So that's really the essence of this whole project. So in a bit more detail, as I said before, the TC plugin init, it's called at the start of type checking. So it's not run every iteration of your type checker. It's just before it starts type checking. So you can use this to set up your type checking context, as we will see later on, just to get some bits and pieces from your Haskell modules that you're interested in. But you can also use it to talk to the outside world. So you can set up an SMT solver or stuff like that, or do something crazy like download a DTD from this website to make sure that all your XML that you're generating in your Haskell program satisfies this DTD. So you
just randomly let your program type check, or no?
Yeah. You can have it look up the moon phase, and if it's a Wednesday, then it says yes. So yeah, you can go wild there. But the TC plugin solve, as I said earlier, this is the interesting bit. That's the piece of code that gets evaluated during these iterations of constraint solving. And then afterwards we stop it, and then we stop looking at the moon or whatever we did to feed our type checking process with. And yeah, we have I/O available in all of this, which is somewhat scary, but also really useful. So this DC plugin solver type, what it gives us, so we have to give this function that takes 3 sets of constraints and gives some result back. So the 3 constraints that GHC gives us, they can be given constraints. So if I write some function that uses sort or something, then if I define sort, I need to say in the type signature that if I get a list of type A, this A needs to have this EQ class instance and an odd class instance for my sort function to work. So that's the constraints that are given by the user or some other thing. There's derived constraints. So again, in the sort example, if I say that I need something of class odd, if we look at the type class definition of odd, we see that it needs the type class EQ. So if we only give this odd type class constraint explicitly, we will see a derived constraint coming from that being an EQ constraint. And there's also stuff like functional dependencies that might give us new constraints that certain types need to be the same, stuff like that. And there's the final one, the actual interesting one for us in this talk. That's the wanted constraints. And that's basically the constraints that GHC hasn't been able to solve yet. So that's what we will be working with. That's what we will be looking at and see if we can solve some of those constraints that GHC throws at us. So what's this result that we have to give back? So there's 2 options, right? So if we look at constraints, we can either say, yeah, these constraints, we can't solve them because there's this 1 constraint or 5 constraints that you gave me, and I just know that these are not solvable because it asks me to show that int is the same type as bool or something crazy. So that's one option. The other option is that we actually managed to satisfy some constraints. So we give back some of these wanted constraints or whatever, along with some evidence that, yeah, these constraints can be solved. And we can also produce new wanted constraints. So I might be able to simplify constraints better than GHC for my tiny domain. And that's where you might want to generate new constraints and not just solve ones. So that's what the second argument is about. Yeah?
What form does the evidence take?
Yeah, so that's a very interesting question that I will not get into in this talk, sadly. So yeah, that's kind of maybe a bit of a lie that I'm telling here. In this talk, I will focus more on sort of recognizing constraints and dealing with them, and not so much about generating evidence that, yeah, I really give you proof that this constraint can be solved. So in essence, I will be just putting unsafe coerces everywhere, but in a very non-bureaucratic, nice way. Yeah, it's, as far as I understand it, it's
So I think
basically,
it
okay.
can be an arbitrary expression
In core.
3.6.
Okay, so yeah. But
You can think of a constraint as having a type, and then the evidence is the term of that type. So if you want to insert arbitrary bits of core code into your Haskell program, that's the way to do it.
yeah. But yeah, that's sadly not something that we will be talking about in this talk. So we'll just say as evidence, just trust us. It's fine. Also, if we look at this result type, so we can consume and satisfy constraints, show that they can be satisfied. But we can also give back new constraints. So what happens if we always just give more constraints than we solve? Then it just has a limit. GHC just, after a couple of iterations, it would just say, yeah, sorry, I'm not going to wait until this finishes. So yeah, it will throw errors like that at you if you're not being careful, and you can increase the limit if you want to, but yeah. So that's how that's dealt with. So coming back to our example of this showing, adding this new constraint that we can solve, that n plus 0 actually equals n. So how can we relate that to the plugin interface that we've seen so far? So yeah, our goal is to show that, tell GHC that this constraint can be satisfied. So first of all, we need to set up our type checker plugin. We need to find these constraints. We need to somehow pattern match on our constraints and fish out those that sort of match this, this pattern. So we need to be able to talk about this type family add, and we need to be able to talk about this constructor 0, which is a promoted constructor even. So we're not talking about the value level 0, but really the promoted type level 0 here. That's something you can do with a bit of code like this, that we look up the module name in which these things are defined. Yeah, it's a bit of bureaucracy, but it's nothing too scary, and you look up a nice blog post by Christian, for example, and then you see how to do this, and it all works, and that's great. So now the more interesting bit. So we need to write this function of type plugin context that we defined ourselves, right? These are our two type constructors that we fished out of our module that we loaded. So we need to take this context, and then we get these 3 sets of constraints. We have to fish out the one that we care about and show that that this constraint can be discharged, and that we can assume it to be satisfied. So that's what this solve constraints function that we wrote does. It just looks at all the wanted constraints, and then it tries to recognize this constraint that we will see on the next slide. And if it manages to find that constraint, then it will say, okay, here's some evidence for it, and we can consider that constraint to be solved. And also note that we have an empty list here because we're not generating any new constraints. We're only solving stuff here. So this solve function, what that looks like, there's a whole bunch of line noise here, and it looks a lot scarier than it is. But really, it's just recognizing this thing. So there's some work that you need to do to deal with these constraints. But basically, if you want to do this yourself, you look at the GHC API, and the Haddock documentation is non-existent. So when you first look at it, you're thinking like, okay, how do I use this? But actually, if you look at the source code, the comments are amazing. So don't worry if you don't see any Haddock documentation if you look at the GHC API, because there is really useful documentation. So yeah, you spend some time staring at a bunch of modules in the GHC API, and then you can see that this constraint here, it corresponds to some predicate that can be hiding in this CT evidence of our constraint, and it's an equality predicate, and in our case, we can get away with what's called nominal equality here. So then we can pattern match on the types that we get. So this is basically like a T1 squiggly line, T2 kind of constraint. So we just pattern match on T1 that is of type, well, actually, I'm switching the things around here. So I expect a type constructor here with an argument and another type. So I'm just trying to pattern match on this thing being add n plus 0. And if I manage to do so, I just say, just trust me. If I recognize that, then I just say, OK, we can consider this constraint as being solved.
Since you already made that glitch, at least on the slide, with flipping the two sides around, does that matter? I mean, can we trust this to catch all relevant equalities?
Yeah.
To match both directions?
So in practice, you do have to be a bit more careful about it. In this example, yeah, we can get by just looking at one case. But yeah, sometimes there is some voodoo about it to, like, in what order you get the constraints, in what order you solve them, or what order you apply the simplifications and whatnot. So it can definitely be a bit unpredictable at times. So yeah, that's one example of type level. Yeah.
I suppose it's possible to get the constraint like nested in in another bigger constraint. So you have to recognize that on one side a list appears nested in a bigger expression, and in the other side you have the same expression but with the list replaced by say the other term of the quality.
You mean like in our equality constraint, we can have more constraints?
You have appending an empty list on the right. It gives you the same list. So I'm imagining a case where that same equality appears in a bigger expression. You have on one side the appending of the list, and on the other side you have just the left at least.
Absolutely. This is not at all complete. We may have to do a bit more work to fish out all the relevant constraints to actually make it work in all cases that we care about. But then it doesn't fit on one slide anymore. But yeah, it's doable. So that was type level natural numbers. Another nice example to have at the type level is type level sets. So we might give an interface to type level sets that looks a bit like as follows, that we have this kind typeset, and we have a way to go from a list of types into the set of types, like from list does for value level types. And then we might sometimes want to take a union of two sets and create a new set. And well, we want these things to behave like sets, so we expect that GHC should be able to recognize these kinds of constraints as being solvable. And yeah, so how might we go about producing such a type level gadget like this? Well, first of all, why would you care? That's also a good question. We can use these type level sets maybe as like a set of effects that we want to track. We might have some kind of indexed monad in which we track all our read file and write file effects or whatever. So we might have some data type that defines an indexed monad, that we have this read operation that reads a file path, and in the index of our index monad, we remember that we have read a file in this action. And similarly, we can do that for writing. If we do something pure, then you would expect the set of effects to be empty. So that's why we have this no effects here. And if we do a bind, the effects of the resulting combination of the monadic computations should give us the union of these two sets of effects. So that's kind of a motivating example as to why you would want to have these type level sets. And yeah, because here we might really only care about sets, not about the order of the effects, not about how many times I've read a file or something. So yeah, that's why you might want to use a set instead of a list. So here's one approach to defining these type level sets. You just define this type level sort function on your types. You can do this with some type family magic, and then you just say, okay, a set of types, it's just the normalized thing of that list of types. So this is a type family that takes a list of types, and then the set of that is just, you sort the list and you get rid of all the duplicates. So then if we have like a list, we start out with a list of int and bool and another list of bool and int, we end up with the same normalized expression. And this is something that's implemented in the type level sets package by Dominic Orchard and Thomas Petricek, which works really well. So there's no need for type checker plugins. It all just works out of the box. One limit of this approach is that, just like with this n+0 case, it works fine if we have concrete lists, but if I say something like, oh, I will give you a union of A, and you require me to give an A, it won't be able to recognize that for arbitrary type variables. So you kind of lose a bit of abstraction possibilities because of the types here if you take this approach, but this is also something that type checker plugins can help in. Here's another approach that we can use, promoted data types, that we just say, okay, these functions that I expected to have, they're just constructors of my data type, which works, kind of. The problem, though, is that since this is a data type, LMs is really treated as a constructor, so GHC also rightly thinks that it's injective, so we can define these type families that where we actually distinguish between two sets that we want to be able to feel that they should be the same. So we can actually write these type families that distinguish between things that we do not want to distinguish between. So a solution to that problem is to not use data types that are promoted, but sort of supply an abstract interface. So we say we have some data type set and no constructors that are visible to the user, but instead we have these type families without any clauses. So these are just closed type families with no definition. So then this type family that we had here, if we try to do this with LMs being a type family, then GHC will complain that this type family is not injective and it won't allow you to distinguish between things that you don't want to distinguish between. So in some Haskell module, you provide this abstract interface, and then your type checker plugin kind of provides the implementation of LMs and union, and maybe a bit more as well. So what sort of the general pattern that you see in these kinds of type checker plugins is that we don't care about all types that GHC gives at us, because we focus at some small domain. So we have this data type, our representation for just those types that we care about, in a format that we can deal with a bit better than just the type, just then this type that GHC gives us. So we translate it to something that we can manage a bit better. So we have to first define what we care about, and then some translation from the type into maybe this expression that we care about, and give back a nothing if we don't care about it. And then we need to define some kind of equality decision procedure that takes two of these expressions and says, yeah, I think these two expressions are the same. Otherwise, it says no. And if you're doing this nicely, you should also provide some evidence that these two things can be regarded as the same. So yeah, a lot of the boilerplate that we saw for the natural numbers example carries over to this example. So again, we have to look up our type families that we care about and pass them around to all the functions that we will be defining later. And here it's mostly the same, except that we now in our function solve constraint, we also give back an answer if we think that it's an incorrect constraint. So previously we only looked at one constraint that we said, yeah, if we see this, then you can discharge it. Here we might also see constraints and say outright, yeah, you can't solve this because we think these two are not equal. So that's a slight difference here. So that's where the TC plugin contradiction is used here. And yeah, so here's a lot of the same boilerplate that, again, here we only care about these equality predicates between types. And then we call our functions that we talked about earlier that fish out the parts of the types that we care about and apply some decision procedure to it to say that whether they are equal or not. And then we give back a result that if they are to be considered equal, we just give this evidence that these should be regarded as equal. If it says false, then we should say that it's an inconsistent constraint and can't be solved. And if we don't see anything we care about, we say nothing. So that's that bit. So a bit more about these expression types. So one option for us here is that we turn this, what we started out with, and basically have the same thing, but just as a value level definition. So actually, if we had this as a, how do you call it, as the promoted data type that we had earlier, we could possibly reuse some code here, but at the expense of the nastiness with injective type families or injective data constructors. So here, yeah, they look very, very much the same. But in reality, you might want to make this a bit more complicated than just this, as we will talk about a bit later. So if we do this, then we can write this quite boring function that recognizes a type. It's just a bunch of pattern matching and fishing out the bits that you care about. So this is like you spent more time reading what functions to call from GHC API rather than thinking about writing this. So it's really straightforward code, this bit. Now this is actually the bit that's interesting, the decision procedure that you apply to this thing that you've thrown away all the stuff that you don't care about, and you're left with these expressions that you want to compare. So in our case, we just take the expression that contains all these types, all these unions and whatnot. We flatten it, get one big list of types, and then we just sort it and nub it. So this is exactly the same as what happens in the type level sets library, but then just in your type checker plugins. And yeah, if we do this, our example index monad, it now has a bit better behavior in terms of type checking results, that if we have this action where we bind two pure actions, it rightly sees that the union of two empty lists is still an empty list. And if we bind a read action followed by a write action, then it shouldn't matter whether I put read file first here or write file first. So this just type checks and everything works nicely. But the big thing that's missing here is how to deal with type variables. So that was that one thing that actually gives you the edge over these solutions with lots of type families to normalize your things. To solve this problem, we can extend our typeset expr data type to also be able to talk about variables, which is straightforward to do that. And we can update our function that recognizes these typeset expressions to recognize variables. It's also easy, but our compare function will suddenly become a lot more interesting. So that's where the hard work is involved. And that's also the interesting bit, that you actually, you want to spend your time on that. So that's kind of a general architecture that you might find when you use these GHC type checker plugins. You have some kind of language, some set of abstract data types. You don't give any constructors because that might allow your users to cheat and see that things are different even though you want to regard them as equal. So you have to keep it all abstract with these abstract data types and abstract type families. And in your plugin, you write some code to fish out these expressions involving these abstract data types and type families. And then you write a function that compares these two expressions and gives back a result. So yeah, if you want to learn more about this stuff, so most of this presentation can also be found in Christian Bay's blog post about this, which is really good. There's a nice paper from quite a long time ago already, I think, by Adam Gundry about using these type checker plugins to talk about units of measure, to make your physics easier or to check your physics homework, I don't know. And then very recently, there's this Torelf plugin. It was presented at this year's Haskell Symposium. That's kind of a type checker plugin to end all type checker plugins, in that you can automate an awful lot of this function. So this is actually, in general, quite difficult. And here they talk about machinery using SMT solvers and whatnot to make that a lot easier. And another use case that I didn't really talk about today is that these type checker plugins, you can also use them to improve type inference. Today we only talked about type checking, making programs that we think should type check, actually type check, versus programs that we think should not have these ugly explicit type signatures, to make type inference for that better, and also with the effect of your type signatures being more readable. You can also use type checker plugins for that, which is also described in this Supermonads paper, which there's a talk about that later today, so do attend that. So yeah, what have we seen so far? That there are situations in which your type checker is not clever enough, and that there's a way out of that problem by just teaching it a couple of new tricks. And when I was learning about this, I found it quite surprising how the boilerplate aspects of it are really not that substantial. It just, a lot of this boilerplate just fits on slides. So it's definitely a lot less scary than I first initially thought, using GHC API and whatnot. And then you're really only left with the difficult bits, writing these compare functions and stuff. What we have not seen, when we had to give evidence, we just cheated and said, trust us, we know what we're doing. So we've not seen today how to do this in a principled way, how to actually make sure that your type checker still does what it does, right? Prevent you from writing bad programs that crash during runtime. And it's very easy to write type checker plugins that make your programs crash, or accept programs that crash. So should you write your own type checker plugins? Yes, because it's a lot of fun. You learn quite a lot of things about how GHC works, how type checking works. So it's a great way to spend a rainy Sunday afternoon, a rainy Sunday afternoon. In practice, should you be writing your own type checker plugins and using them in production code? Probably not, because it's just too easy to write something that, like, unless you want to. If you are thinking of doing that, you might as well use unsafe GUIs everywhere, which is also a lot of fun, but maybe not a good idea. So yeah, that was my talk.